Okay, today we are going to discuss about the Lorentz transformation. We left where we said that the Galilean transformation fails if constancy in speed of light is assumed. Okay, so we will start with the part 2 of that Lorentz transformation. So part 2 of our Lorentz transformation, derivation for Lorentz transformation. Now let us consider, instead of your x dash equals x minus vt, which we considered in Galilean transformation, now we will change it by multiplying a constant factor gamma to this x minus vt. Okay, so this way we will try, and then later using boundary conditions we will be able to determine this gamma, okay, which we just arbitrarily multiplied constant that we will find out. Okay, now let's use the inverse transformation. Okay, using inverse transformation we can write x in terms of x dash as well, transformation. So let's use the inverse transformation. Using inverse transformation, this x dash can be written as x, right? Gamma is the constant, so it will remain as it is. Then your x dash will be x will be now x dash, minus is plus. Now v is constant, uniform velocity. We have already discussed that s dash prime is moving with uniform velocity v, so that remains the same. And now t becomes t dash. Okay, so this is the inverse transformation we are writing for x to x dash. Okay, since the motion is along positive x direction, y dash will remain as it is, y dash will remain as y, and there will be no change. Z dash will remain as z, and t dash is also t, right? Okay, now let us substitute for the value of x that we have written here. So in this equation, x dash equals gamma times x dash, x equals gamma times x dash plus vt dash. So here in place of this x dash we are going to substitute this equation. Okay, so it will be little lengthier, but it's easy. X equals gamma times what for x dash, substituting gamma times x minus vt from this equation, right? Then plus vt dash, as usual you can see vt dash, sorry, this was t becomes t dash here. Okay, and this is our equation. Okay, now we'll open this bracket, gamma square times x minus vt plus gamma times vt dash. Okay, rearrange it, gamma vt dash equals, we got x here, minus gamma square x minus vt. Okay, then this can be open, the bracket you can open, gamma square plus gamma square vt, that is gamma square vt, and you take the coefficient, you take the x out, so you got right 1 minus gamma square, right? This is what we got, gamma vt dash. Now let us divide both the sides, left hand side and the right hand side, both with a factor of gamma times v. Okay, here also gamma times v. If we divide that, then the left hand side we got as t dash. Okay, and the right side we got this as gamma times t, right? 1 gamma square and gamma cancelled, you got gamma, v cancelled, you got t, plus x times, you got 1 minus gamma square divided by gamma v. So the second term we just divided the gamma v, right? Now as we said, c has to be same speed of light. To keep the invariance of speed of light constant, we you need to use the initial conditions to show that under what condition this c will remain invariant, right? So for that reason we are using the initial condition. So our initial condition was, if you know, they were coinciding. Okay, the s and s dash frames were coinciding with each other initially, so we can use that x equals x dash equals 0 and t equals t dash equals 0, right? That was the initial condition for both the frames. Now in frame of reference S, the x coordinate of the light pulse can be written as x is equal to ct. You know that, right? So in time t, the distance traveled by light will be x equals ct, right? And in s dash frame, it has to be x dash equals ct dash, right? Okay, now what we are going to do, we have the values x dash is equal to x dash. As per the new transformation, we wrote it as gamma times x minus vt. Okay, and t dash. Okay, we can write t dash that you got here. You can see that t dash value also, so we can substitute t dash equals, you can see gamma t plus x times this bracketed term, which I'm writing again, gamma t plus x times 1 minus gamma square, 1 minus gamma square over gamma v. Okay, so these two values we will substitute here. X dash is equal to ct dash. Okay, so our equation will be, for x dash it is gamma times x minus vt, that's for x dash substituted, and then c, and for t dash we have gamma t plus x times 1 minus gamma square divided by gamma v. Okay, open and make it simple. So gamma x minus gamma vt equals c gamma t plus cx times 1 minus gamma square divided by gamma v. Right, here you can again substitute x equals ct whenever needed, wherever needed. Gamma x minus gamma vt equals gamma x plus cx 1 minus gamma square divided by gamma v. Right, make x the subject. You can solve by your own from this step onward. Gamma vt times gamma v divided by c times 1 minus gamma square, because you can cancel these two terms and then cross multiply and solve it, right? So this way you got the x value. You can just simplify it, writing minus gamma square v square t divided by c minus c gamma square, right? Cross multiply, so you got x times c minus c gamma square, right, equals minus gamma square v square t. Okay, rearranging cx minus cx gamma square equals minus gamma square v square t, implies this is x is equal to ct, substitute, so c into ct, that gives you c square t, and then minus here also you can write ct, so c square t times gamma square equals minus gamma square v square and t, right? So this way now you can take t common from for all these terms, and you can cancel t from all the terms, right? So we are remained with c square minus c square gamma square, which equals minus gamma square v square, right? Okay, so here you can write c square minus v square, okay, taking the coefficients of gamma square out, equals c square, right? And then make gamma square the subject. You got c square divided by c square minus v square, that dividing the numerator and denominator both by c square, right? So I will divide this by c square and this whole thing by c square, that's okay. So you got 1 divided by 1 minus v square by c square, right? So basically we got gamma is equal to 1 divided by square root under 1 minus v square by c square. Okay, we told that we can calculate the random multiplier gamma we used in the transformation, right, using initial conditions. So our initial condition was x dash equals x equals 0 and t dash equals t equals 0. Using that we could derive this constant factor is known as our Lorentz factor. Okay, that's a very important factor to determine the variance in your time and the position. Okay, so here again we can write the equations. So x dash equals gamma times x minus vt. You have the gamma value, so this is our first, okay, transformation. Similarly, and your y dash remains y, z dash remains z, because the motion is along x direction, right? And your t dash will be gamma times t, that we have already derived this, and x times 1 minus gamma square over gamma v, right? But you can substitute the gamma value, which is 1 divided by square root under 1 minus v square by c square, and just simplify it, multiply and see, simplify it, whatever can be cancelled you cancelled it out, and finally you will reach to this value, gamma times t minus vx divided by c square, right? This is what you will get after substituting the value of gamma, right? Okay, and this, okay, so x dash is gamma times x minus vt, y dash is y, z dash is z, because there is no change in y and z direction, but t dash you got gamma times t minus vx by c square, right? But if you want to check how this Lorentz transformation will behave under the condition when the v is very less than c, right, when the speed is non-relativistic or much less than c, then we can say that v by c tends to 0. Okay, so here under this condition, if you check your x value, you got your gamma, basically your gamma here, which is 1 divided by square root under 1 minus v square by c square. So you got this to be 0, so 1 minus 0 you got, so 1 by 1, which is 1, right? So if I'll substitute it here, you got x dash equals gamma times x minus vt, which is x dash equals x minus vt. So our x dash equals x minus vt. Again you get back to the Galilean transformation by considering gamma is 1. Okay, and your t dash will be, you can see, t minus vx by c square, v by c here is tending to 0, so you got this as 1 multiplied with t minus 0, which is t. So you got t dash equals t, again back to your Galilean transformation. So basically Lorentz transformation is the most accurate transformation, and it works very well with relativistic speed, or when the speed of light is, I mean speed of the object is comparable to the speed of light, but when it is very less than speed of light, then it reduces to the Galilean transformation, right? Thank you for watching.